Hi, everybody. Today I'd like to discuss several data analytic issues. I'll begin with an important analysis that we typically see in experimental design when we're designing an experiment. And here I'd like to explain the difference between what is known as a main effect and an interaction. And this comes from an analysis known as analysis of variance, or ANOVA. So suppose that we have some dependent variable. I'd like to know how people perform on a certain task. And I think that dependent variable, the performance on the task in question, is a function of two factors. Say one factor is the mood that the person is in, if they're in a good mood or bad mood, and how much of an expert they are. Are they an expert or a non-expert? And so here what I've written is if you like, the generic mathematical formulation of that relationship. So the dependent variable is a function of the main effect of mood plus the main effect of expertise plus the interaction effect between mood and expertise. And you may not know at this point what an interaction is. It'll become abundantly clear by the time that we're done with today's lecture. So as I said, we have y is a function of a and b and the interaction between a and b. And so here what I've written here is all of the possible statistically significant effects that could come from an ANOVA. And again, bear with me, you may not know at this point what I mean. The ones and the zeros simply connote whether the effect in question is statistically significant or not. So we could have 8 possible combinations, because if there are if mood could be statistically significant or not, expertise could be statistically significant or not, and their interaction could be statistically significant or not. So it's 2 to the exponent 3, 2 times 2 times 2. So there are 8 combinations. So this one, for example, 1, 1, 0 would mean that there is a main effect for mood, a main effect for expertise, but there is no interaction effect. The 0, 0, 0, or let's say this one, there is no main effect for mood, there is no main effect for expertise, there is no interaction effect. 1, 1, 1 would mean all of the possible effects are significant. And so what I'm going to do over the next few minutes is show you how we interpret each of these findings pictorially. But before I do that, let me just expand this framework to, let's suppose you had 3 experimental factors. So if you had 3 experimental factors, then it would be some dependent variable y is a function of the main effect of factor 1, A, the main effect of factor B, the main effect of factor C, all possible two-way interactions. So the interaction between A and B, A and C, and B and C. And then there is a 3-way interaction effect. So this is exactly what we're doing when we're testing ANOVAs. Now, when we're talking about a factorial design, say a 2 by 2 factorial design, this means that A, which is one of the independent factors, is going to have one of 2 possible values, let's say high mood and low mood, and B is going to have one of 2 possible values, let's say expert and non-expert. That's what we mean by a factorial design. So now we've set the ground for what we mean by an interaction effect and a main effect. So now I'm going to systematically go through how each of these different possible patterns of statistical effects, or lack thereof, would look like pictorially. So let's go through that. So let's go through here the first one. So this is the pattern 1, 1, 0. What does that mean? There is a main effect for mood, there is a main effect for expertise, but there is no interaction effect. So if y is plotted on the y-axis, mood here is either low or high, and this is the line for the experts and the line for the non-experts. What does that mean? There are 4 means that you're looking at. So for example, this mean is for people who are experts and are in low mood. This mean is for people who are non-experts and in low mood. This mean is for people who are in high mood, non-experts, and high mood and experts. Okay, so what you're doing is you're showing now these effects. So if there is a main effect for mood, that means the mean of the low, so this mean with this mean, which is right here, is statistically, in this case, lower than the mean for the highs from here to here, meaning that irrespective of which condition of expertise you're in, it is always the case that people in low mood score worse on Y than people in high mood. And that's known as a main effect for mood. Precisely because you could say, irrespective of the value of whether you're non or low high expert, the low mood people score worse than the high mood people. So there's a main effect for mood. And then there's also a main effect for expertise. Why? Because this is the line for the experts and this is the line for the low experts. So the mean of this to this is here. The mean for this and this is here. So the line of experts is higher than the line of non-experts, irrespective of whether you are low mood or high mood. In other words, expertise is a main effect independently of the score of the one's expertise score. Okay, so this is the first of many possible findings. Let's look at the next one. This is, there is no effect for mood, no main effect for mood. There is a main effect for expertise, but there is no interaction effect. So let's start with this one. Here is one mean for low. Here's the other mean. The mean of these two is here. The mean of these two is here, meaning that the average mean score of people in low mood and the average mean score of people in high mood is the same. Therefore, there is no main effect for mood. But the expert line is higher than the non-expert line, so there is a main effect for experts. And there's no interaction effect because each of those two things that I said occurs independently of the score on the other factor. And again, it might be a bit confusing now, but it'll all become clear as we go through. This is the one where you picked up no effect whatsoever for anything. There's no main effect for mood, no main effect for expertise, no interaction effect. Now, the two lines here, I showed them to be different, but assume that they are equal. Like statistically speaking, these two lines are the same. Okay, so if you look at low mood, the mean is here. High mood, the mean is here. The mean is here. So there is no main effect for mood. There is no main effect for expertise. Why? Because the two lines are equal. They're the same. And then there is no interaction because those two previous statements hold true independently of the levels of the other factor. Let's go on to the next one. This one, there is a main effect for mood. There is no main effect for expertise because, again, I'm showing these to be different, these two lines, the expert and non-expert line, but, you know, statistically speaking, they're the same, and there is no interaction. So how do we interpret that? The people in low mood, their mean is here between these two points. The people for high mood, their mean is here, and therefore this mean is lower than this mean, so there is a main effect of mood. People in low mood score worse than people in high mood. I mean, it could have been the other way around. It could have been people in high mood score lower than people in score higher than people in high mood. Then the lines would have been the other way. But all that we mean by a main effect for mood is that one condition of mood scores higher or lower than the other condition, and that's what we see here. There is no main effect for expertise because these two lines are the same, and there is no interaction, again, because each of the statements for mood and for expertise holds true independently of the level of the other factor. Now the next one is going to be the first interaction effect that we see. By the way, originally when I had given you the, I had wrongly put non-expert line here, but then that would mean that both arrows are pointing to experts. What I mean, so I corrected it. The expert line is here, this one. The non-expert line is this one, right? So make that change in your slide 6, please. In any case, you have no effect for mood, no effect for expertise, but you do have an interaction effect. And now I think it'll become abundantly clear what I mean by an interaction effect. So let's look at the no effect for mood. The mean of this and this for low mood is here. The mean of this and this for high mood is here. These two means are equal, so there's no main effect. So when you average out the two means for the low level mood and the two means for the high level mood, you don't get a difference between these two means. And if you look at the expertise line, the mean is here. So this is the line. The mean for the non-experts is here. There is no difference between experts and non-experts, so there is no main effect. But there is an interaction. Why? Because in the low mood condition, experts score statistically higher than non-experts, and in the high mood condition, it's reversed. The non-experts score higher than the experts. Therefore, which pattern is the one that's operative depends on the factor of the other, the level of the other factor. Therefore, there is an interaction between the two factors. You get it? It depends. Depending on the level of mood determines whether experts score higher or non-experts score higher. That's the definition of an interaction effect. Let's look at the next one. Now, this is called a crossover interaction. So you get, in a crossover interaction, you get no main effects, but you get an interaction. Now, this is if you like, a fan-out interaction. It's 0, 1, 1, y. There's no main effect for mood. There is a main effect for expertise, and there is an interaction. Let's go through it. So the mean between this one and this one is here, and again here I'm showing these to be different, but statistically these two means are the same. So there is no statistically significant difference between this mean and that mean, which is right here. The mean between here and here is somewhere here, so there's no difference. So the average mean score for the people in low mood and the average mean score of people in high mood is the same. That's why you get no main effect. But the line for the experts, the mean is here. The line for the non-experts, the mean is here. Those two lines are not equal to each other. So there is a main effect for expertise and there is an interaction. Why? Because under low mood, there is no statistical difference between the two expert groups. But under high mood, there is a huge difference between the two groups. So it depends. So whether there is an effect or not on expertise depends on the level of mood. And hence, in this case, it's a one-way fan-out interaction. Let's do another one. This one has a main effect for mood, no main effect for expertise, and there is an interaction effect. So let's look at that. Here is the mean of the low mood group is here. The mean for the high mood group is here. The difference between this one and this one is statistically significant. Therefore, there is a mean effect of mood. Low mood people on average score higher than high mood people. There is no effect of expertise, this one. Why? Because the mean of this line is roughly here. The mean of that line is the same. So your level of expertise doesn't have any effect across the two mood conditions. But there is an interaction. Why? Because under low mood, the experts score higher than the non-experts. But under high mood, the non-experts score higher than the experts. And therefore, the manner by which expertise manifests itself is different. It depends on the level of mood. And therefore, there's an interaction. Let's look at the next one. This is the last one. This one, all of the statistical effects came out to be significant. There's a main effect for mood, there's a main effect for expertise, and there's an interaction effect. So let's look at that. In the low mood condition, here's one mean, here's another. That's the average mean score. Under low mood, the average mean score across these two is here. And again, these I showed them to be different, but they're statistically the same mean, if you like. This is a fan-out interaction, but in the other way from the one that I showed earlier. So there is because this mean here is higher than this mean here, there's a main effect of mood. In this case, low mood people score higher on average than high mood people. There is a main effect of expertise because the mean score of the expert line is here, the mean score of the non-expert line is here, so the expert line is statistically higher across the two conditions of mood, statistically so therefore there's a main effect for expertise. And there's an interaction. Why? Because in the low mood condition, experts score higher than non-experts, but in the high mood condition, the two means of expertise are not different from each other. Therefore, whether expertise is statistically significant or not depends on the mood condition, and therefore there's an interaction. So what I've done here for you is shown you how to interpret pictorially all of the different possible effects that could ever come up in a 2x2 factorial design, where you have two main effects and one two-way interaction. Now imagine that this can get very complicated when you're dealing with more factors, so there are higher order interactions and so on and so forth. But at least by showing you this example, it gives you a sense of how to think about main effects and interactions. And then the last slide that I want to talk to you about is a few sort of additional hodgepodge of things. I've already talked to you guys about some of these. So Cronbach's Alpha, if you like, is where you have, let's suppose you're measuring some, let's say, attitude towards the ad. You show people an ad and then you want to measure their attitude towards that ad. And you measure their attitude towards their ad using many different items. Interesting, uninteresting, boring, fun, whatever. And the idea is that each of these items is measuring the same underlying construct. It's measuring people's attitude towards the ad. So what you'd like to do, let's suppose you had 5 measures that are measuring attitude towards the ad. You'd like to take these 5 measures and collapse them onto one average score. In other words, if I'm collecting data from 100 people, I don't want to be carrying 5 data points for each of the participants. Rather, I'd like to collapse the 5 measures of attitude towards the ad onto one aggregate score of attitude towards the ad. But I could only do that if I confirm that the 5 items that are supposedly measuring the same underlying construct are actually all moving in the same direction. And so what I do in this case is I do a Cronbach Alpha analysis. That's basically a measure of inter-item correlation. So if that number comes out to be high, and we just have a standard that we set it at 0.7, if the Cronbach Alpha is greater than 0.7, that's your green light that you can go ahead and collapse the 5 items onto one average score, so that when I'm analyzing your data, I don't need to be looking at how you answered each of the 5 questions. I just take an average of those. It becomes your overall attitude towards the ad score. Now let's suppose you didn't get that. Let's suppose you got a Cronbach Alpha that's 0.43. Well, that means that there is at least one culprit among the 5 items that's causing the inter-item score to be lower. So then usually here what you would do is you would go through the data, and let's say you find that, I think item 3 doesn't seem to be moving in the same direction as the other items. Then you would remove that item, run again the Cronbach Alpha with the 4 other items. If now the Cronbach Alpha jumps from the low number that it was at up to, say, 0.8, then you know that was the culprit, and in that sense you've purified your scale. Okay, so Cronbach Alpha is something that is used when you are using in your questionnaire, in your post-experimental questionnaire, you're using multiple items to measure one underlying construct. Before you collapse all those measures onto one final score, you need to conduct the Cronbach Alpha. Then next, I wanted to talk about something called the stepwise regression. Usually when you run a regression, let's say you think that your how well you do at school is a function of variables A, B, and C. So then what you would do is you would run a regression and you would try to estimate what is the coefficient of these regressions to know how does A move with Y, how does B move with Y, and how does C move with Y. And in this case, you're imposing the structure of the model. You're saying that Y is a function of these three predictor variables, and then you're now going to estimate the strength of that relationship by estimating the coefficient of each of those variables. But that's in a full model regression. A stepwise regression is something different. Basically, it says, no, I'm not going to impose the structure of the model. Rather, I'm going to let the data decide for me what is the optimal model. And so there are two ways you could do that. You could start with the full model and then through backward elimination work backwards, eliminating variables that don't have much explanatory power. Or you could start with the simplest, no predictors, and then bit by bit through forward the forward iterative process, you could add variables until you think that the addition of additional variables doesn't increase sufficiently the explanatory power. The idea basically is that your R squared, how much variance is explained by your model, is always going to get higher if you add more variables. But the question is, the tension is, how much more explanatory power do you gain by adding more predictors? So for example, if only having Y is equal to A has an R squared of 0.6, okay, and then adding an extra 2 predictors only increases it to 0.61, then the addition of 2 additional variables has only slightly increased the explanatory power, and therefore simply having that one variable is sufficient. So that's the tension. That's what if you like, the stepwise regression is doing. It is looking at the trade-off between how much explanatory power and the simplicity of the model. Okay. So let's look, say, at a forward stepwise regression. So there are 3 possible simple regressions. Y could be explained by A, or explained only by B, or explained only by C, or all possible 2 variable models would be Y is explained by A and B, Y is explained A and C, Y is explained B and C, or this is the full model. Y is a combination of A, B, and C. And so what a stepwise regression would do is it would sort of go through these models, and using a criterion, it will say, you know what, in light of the tension between how complicated I want the model to be and how much explanatory power the model gives me, this is the optimal model. And then it would stop here. So it is letting the data decide what is your optimal model, whereas typically in a regression model, you stipulate what the model should be, and then it estimates for you the strength of the coefficients. So there you have it, folks. These are some of the important statistical lessons that I wanted you to at least appreciate. And as I said before, for all of the MBA students who are listening to this lecture, please try to take as much of these formal analytical courses, because as I said, that's where you really get a lot of the bang for your buck. All right, folks, hope you enjoyed this technical lecture. Have a great long weekend. I'll talk to you soon. Cheers.